Section 1 Introduction. We're here to introduce a new learning approach known as in-context learning, ICL. This method is a game changer as it allows large language models, LLMs, to carry out tasks using only a few examples, without needing to adjust the model's parameters. This is a significant departure from traditional machine learning, which usually requires training models on extensive datasets of labeled examples. ICL is particularly beneficial in areas where labeled data is hard to come by or costly to acquire, as it significantly reduces the need for such data. However, understanding and improving ICL's effectiveness isn't without its challenges. One of these is the sensitivity of LLMs to the quality of the in-context examples provided. If these examples don't accurately represent the task at hand, the model may struggle to learn effectively. Research has shown that using the BM25 algorithm or pre-existing sentence embeddings to pull examples from the training set can significantly improve ICL's performance over random selection. Another strategy involves training dense retrievers based on feedback from LLMs, which has shown promising results in semantic parsing, cross-task prompt retrieval, and unified multitask retrieval. Despite these advancements, existing methods either focus on a relatively small language model or fail to effectively use the detailed feedback information from LLMs. To address this, we're introducing a new framework, the LLM Retriever, LLM-R, designed to retrieve high-quality in-context examples for large language models. Our framework ranks an initial set of retrieved candidates based on the likelihood of the correct outputs according to the LLM. We then train a reward model using a crossencoder to capture the detailed ranking signals from the LLMs. Finally, we train a dense retriever using a bi-encoder and knowledge distillation. The reward model is key in providing more informative soft labels suitable for distillation, rather than using one-hot labels constructed heuristically. This process can be repeated multiple times by retrieving a new set of candidates based on the latest dense retriever. To evaluate our framework, we've put together a diverse set of 30 natural language processing (NLP) tasks, spanning 9 categories, including question answering, natural language inference, common sense reasoning, and summarization, among others. Our experimental results, obtained using Llama 7B, show that our model improves ICL performance by an average of 7.8% compared to random selection. We've observed similar improvements on held-out tasks and LLMs of varying sizes. Further analysis shows that the top retrieved examples often share similar input patterns or the same labels as the testing example. Our model is particularly effective for classification tasks with ample training examples. However, tasks like closed-book question answering and common sense reasoning rely more on the inherent capabilities of LLMs and are less sensitive to the quality of in-context examples. Section Summary. In this section, the authors introduce the concept of in-context learning, ICL, which allows large language models, LLMs, to perform tasks with few-shot examples without updating the model parameters. They highlight the advantages of ICL in domains with limited labeled data and discuss the challenges associated with it, such as the sensitivity of LLMs to the quality of in-context examples. The authors propose a novel framework called LLM-R, LLM Retriever, that retrieves high-quality in-context examples for large language models, resulting in improved performance compared to random selection. Section 2 Related Work. We're going to discuss some related work in the field of in-context learning, a fascinating feature of large language models, LLMs, like GPT-3, GPT-Neo, and Llama. This feature allows these models to carry out a variety of tasks based on a few examples, without needing any adjustments or fine-tuning. This has sparked a lot of interest in the research community. There are 2 main areas of research in this field. The first is trying to understand how in-context learning works. Some researchers see it as a form of implicit Bayesian inference, while others view it as a type of meta-optimization. The second area of research is about finding the best ways to select and design in-context examples for these models. Recent studies have found that using the BM25 algorithm or fine-tuning dense retrievers based on feedback from the LLM can enhance in-context learning. Our work also falls into this category, as we're proposing a new training method. We're also looking at how in-context examples interact with each other. We're using determinantal point processes and sequential decision-making as initial explorations. In contrast, structured prompting allows us to bypass the limitation of input context length and increase the number of in-context examples to thousands. Dense retrieval is another approach we're using. It's a popular method for retrieving information that uses dense vectors to match queries and documents semantically in a latent space. This method is more powerful than sparse retrieval methods like BM25 because it uses pre-trained language models to learn relevance functions and can potentially overcome vocabulary mismatch problems. Various techniques, such as hard negative mining, knowledge distillation, and continual pre-training, have been proposed to improve the performance of dense retrieval. Finally, we're exploring retrieval-augmented LLMs, which combine the generative power of LLMs with the ability to retrieve relevant information from external sources. This approach could improve the factual accuracy of generated texts, keep LLMs updated with the latest knowledge, and provide a natural way for source attribution. For in-context learning, the aim of retrieval augmentation is to enhance the performance of LLMs on downstream tasks by retrieving informative examples. Section Summary. In the related work section, the paper discusses two areas of research in the field of in-context learning. The first area focuses on understanding the underlying mechanism and principles of in-context learning, with different perspectives such as implicit Bayesian inference and meta-optimization. The second area explores strategies for selecting and designing in-context examples, including using the BM25 algorithm or fine-tuning dense retrievers based on language model feedback. The paper also mentions other relevant techniques such as structured prompting, dense retrieval, and retrieval-augmented language models. Section 3 Preliminaries. In this section, we'll give a quick overview of the problem we're trying to solve, which is in-context example retrieval. Imagine you have a test example from a specific task and a set of K in-context examples from a predetermined pool. We use a fixed language model to predict an output through a process called autoregressive decoding. The main goal of in-context example retrieval is to find K examples from the pool that will make the predicted output as close as possible to the actual output, based on certain task-specific measurements. In our study, the example pool is a combination of the training sets for all the tasks we're evaluating. Simple solutions might involve using the BM25 algorithm or existing text embedding models to find examples from the pool, treating the test example as a search term. Even though these methods are simple, they've been shown to work better than just randomly selecting examples. However, our approach is to create a dense retriever specifically for in-context example retrieval, using feedback from the language models. Our proposed framework is shown in the figure. The training process has three stages: creating training data based on an initial retriever and feedback from the language model, modeling rewards, and training dense retrievers by distilling knowledge from the reward model. When it's time to use the system, the trained dense retriever finds in-context examples from the pool, and these examples are used by the language model to generate the output. To generate training data, we start by retrieving the top N candidates from the example pool using an initial retriever, given an example from the training set. The example pool contains training examples from a variety of tasks. We make sure to exclude the example itself from the retrieval results. In our study, we use the unsupervised BM25 algorithm as the initial retriever. The search term only includes the input, while each retrieval candidate is a combination of the input and the output. This setup matches the test time scenario, where the actual output isn't available. We expect that the top N candidates will include some positive examples and hard negative examples. To evaluate the quality of the retrieved candidates, we use feedback signals from a fixed language model. Specifically, we rank the candidates in descending order based on the log likelihood of the actual output. This is calculated using the conditional probability of the actual output given the input and the ith candidate. This calculation only requires one forward pass and doesn't depend on any task-specific measurements, despite the autoregressive nature of language models. This can help reduce the inference cost of language models in practical applications. Section Summary. In this section, the authors introduce the problem of in-context example retrieval, where the goal is to retrieve a set of examples from a pool that are most similar to a given test example based on some task-specific metrics. They compare straightforward methods like BM25 and text embedding models to retrieve examples from the pool, and propose a framework that leverages feedback from language models to learn a dense retriever customized for in-context example retrieval. The framework involves three stages: generating training data, reward modeling, and training dense retrievers. At inference time, the trained dense retriever is used to retrieve examples from the pool, which are then fed to the language model to generate the output. Section 4.2 Reward Modeling. We're proposing a method to better understand the preferences of language learning models, LLMs, when it comes to selecting the best candidates. This involves training a reward model that uses a cross-encoder. For each training example, we select one positive example from the top-ranked candidates and a set of hard negative examples from the bottom-ranked ones. The reward model takes these examples as input and produces a score. It's trained to minimize a certain loss, which is calculated using a formula that involves the scores of the positive and negative examples. It's important to note that this reward model is only used to guide the dense retriever and has access to the correct label, which isn't available during testing. This is a key difference from the re-ranker in the ad hoc retrieval setting. Compared to the bi-encoder-based dense retrievers, the reward model allows for full interaction between the inputs and can therefore serve as a teacher model. To make the process more efficient, the dense retriever is based on the bi-encoder architecture. We calculate a low-dimensional embedding for a given query by averaging the last layer hidden states. Similarly, we get the embedding for the candidate by taking the combination of the candidate's inputs. The matching score is then calculated as the temperature-scaled cosine similarity between the query and candidate embeddings, where the temperature is a hyperparameter. In this study, we use a shared encoder for both the query and the retrieval candidates. The dense retriever is trained to learn from the reward model. We use the KL divergence loss to measure the difference between the reward model distribution and the retriever distribution. This loss is only calculated over the hard negatives for efficiency. To include the in-batch negatives, we also add a contrastive loss by treating the candidate with the highest reward as the positive example. The final loss function is a weighted sum of the contrastive loss and the knowledge distillation loss, where the weight is a constant that controls the relative importance of the two losses. As shown in the figure, the retriever trained in one iteration can be used to retrieve candidates for the next iteration. In the first iteration, the candidates are retrieved using BM25. This iterative training approach allows for the improvement of retriever quality by mining better positive and hard negative examples. Section summary. To capture the preferences of language models, LLMs, and provide supervision for dense retrievers, a cross-encoder-based reward model is proposed. The reward model takes input from the top-ranked positive examples and bottom-ranked hard negative examples, and is trained to minimize a cross-entropy loss. The dense retriever, based on a bi-encoder architecture, is trained to distill knowledge from the reward model using KL divergence and contrastive loss, with the retriever trained iteratively to improve quality by mining better examples. Section 4.4 Evaluation of LLM retrievers. In this section, we'll discuss how we evaluate the performance of language model, LLM, retrievers. Here's how it works. For a given test example, we calculate its embedding using the trained retriever. We then select the top K candidates from a pool as the K-shot in context examples. These examples, along with the test example, are fed into the LLM. This process is depicted in the accompanying figure. The way we generate the final prediction depends on the type of task the test example represents. For classification tasks, we use a method called greedy search with constrained decoding to ensure the prediction is a valid class label. For multiple choice tasks, we rank all the choices based on their average token level log likelihood score. The choice with the highest score is selected as the model's prediction. For generation tasks, we use a greedy search without any constraints. To evaluate the accuracy of the prediction, we compare it with the actual answer using metrics specific to the task. In our experiments, we used 30 publicly available datasets from 9 different categories for training and evaluation. These datasets were based on FLAN and Uprise. However, our work differs from these in that FLAN is focused on fine-tuning language models to follow instructions, while Uprise is designed for cross-task retrieval. To test how well the models can generalize to unseen tasks, we excluded 4 datasets from the training process. We created a retrieval pool by combining all the training examples, which resulted in about 6.3 million examples. For each dataset, we used a maximum of 30,000 examples for training and 10,000 for evaluation to reduce the cost of LLM inference. We reported the average metrics in each task category for evaluation. The specific metrics used for each dataset can be found in the accompanying table. In our main experiments, we used Llama 7B as the default LLM for candidate ranking and task evaluation, unless stated otherwise. The reward model was initialized with Electra base and the retriever with E5 base. Our baselines included zero-shot prompting, K-means clustering, random selection, BM25, and 2 off-the-shelf dense retrievers, namely SBERT, all MP NetBase v2, and E5 base. Except for zero-shot evaluation, we retrieved 8 in-context examples for each test input. More details about the implementation and training hyperparameters can be found in the appendix. Section summary. In the evaluation of LLM retrievers, we compute the embedding of a test example and retrieve the top candidates from a pool of examples. The input to the LLM is the concatenation of the retrieved examples and the test example, and different decoding strategies are used depending on the task type. For quantitative evaluation, the prediction is compared with the ground truth using task-specific metrics. In the experiments, we use 30 publicly available datasets for training and evaluation, and we hold out 4 datasets to test the generalization ability of the models. The retrieval pool is created by taking the union of all training examples, and we report average metrics for each task category. Section 5.2 Main Results. In Section 5.2, we discuss the main findings from our experiments. The results show that the simple BM25 algorithm is a strong starting point, consistently performing better than a random selection strategy. This observation is in line with previous research. After the first round of training, our proposed model, which we call LLM-R, performs better than all the other baseline models. This improvement is achieved by training on candidates retrieved by the BM25 algorithm. The performance score increases from 62.1 to 65.7. In the second round of training, we include positive and hard negative examples from the first iteration of LLM-R. This increases the average score to 66.5, a slight improvement of 0.8. However, further iterations do not lead to significant improvements, suggesting that the model has reached its peak performance. In Section 6, we delve deeper into the performance of LLM-R across different tasks, language models, and model variants. Unless we state otherwise, when we refer to LLM-R, we mean the model after 2 rounds of training. In Section 6.1, we explore several variations of LLM-R to understand the contribution of each component. One variant, which we call with-O reward model, removes the knowledge distillation loss and results in a slight drop in the average score by 0.8. This suggests that the reward model is a key component for the performance of LLM-R. We also experiment with a variant inspired by replug, which uses the log likelihood from language models as the reward for distillation. Although this variant performs better than the with-O reward model, it still falls short of our method by 0.5 points. We think this might be because the log likelihood of language models may not be well suited for knowledge distillation with KL divergence. Changing the retriever initialization from E5 to BERT results in a slight drop in performance, but not as significant as in the ad hoc retrieval setting. In Section 6.2, we assess the generalization ability of LLM-R from 2 perspectives. First, we test whether the trained retriever can find good in-context examples for tasks that it has not seen during training. Second, we test whether a model trained with one language model can generalize to other language models that vary in size and quality. The results show that LLM-R performs better than the second best model E5 base by an average of 5.4 points on 4 held-out tasks. This suggests that LLM-R can generalize to tasks it has not seen before. However, there are training datasets that share the same task category as the held-out ones, such as QNLI and SNLI, which are both for natural language inference. A more challenging setting would be to test on non-overlapping task categories, which we plan to explore in future work. We train the LLM-R model with Llama 7B. To assess its generalization ability across different language models, we test it on 3 other models, namely GPT-Neo-2.7b, Llama 13b, and GPT-35 Turbo. The results show that LLM-R consistently performs better than the BM25 baseline for language models with parameter ranges from 2.7 billion to tens of billions. Notably, the improvements are particularly significant for smaller language models, possibly because they are less powerful and therefore need higher quality examples to perform in context learning. Section Summary. The main results of the experiments show that the BM25 algorithm serves as a strong baseline, outperforming the random selection strategy. The proposed model, LLM-R, outperforms all baselines after the first iteration, and further iterations do not yield substantial improvements, indicating convergence. The analysis reveals that the reward model is crucial for the performance of LLM-R, and LLM-R demonstrates good generalization ability across different tasks and LLMs. Section 6.3 When does LLM-R work and when does it not? We're going to discuss when our model, LLM-R, works well and when it doesn't. Usually, we'd give a single score to compare different versions of the model, but this can be misleading. It can hide the fact that LLM-R performs better on some tasks than others, and in some cases, it might even perform worse. We've divided the tasks into 2 categories. Some tasks are knowledge-intensive, meaning they require common sense, complex reasoning, or memorized facts to solve. For these tasks, the improvements made by LLM-R are generally smaller than the average, with the natural questions, NQ, dataset being the only exception. This makes sense because these tasks depend heavily on the model's ability to reason and memorize knowledge. In the case of the NQ dataset, we found that some of the training and test sets overlap, meaning some test questions are rewordings of training questions. Despite this, we decided to keep the NQ dataset in our evaluation because it's a widely used benchmark and the remaining unique questions are still valuable. Another interesting case is the Squad V1 dataset, where LLM-R performs worse than a random selection. We found that many questions in Squad use the same passage as context, which often leads to LLM-R retrieving examples with little diversity. This could explain the drop in performance. For the Sentiment 140 and MNLI datasets, our model helps by finding examples that have similar input patterns to the test example. On the other hand, the PIQA dataset requires common sense knowledge and doesn't benefit much from the examples retrieved. Another important part of our framework is choosing the right LLM for generating training data and evaluating tasks. During training, the LLM is crucial for ranking the retrieved candidates and providing feedback for the reward model. During task evaluation, the LLM is used to generate the final predictions. We tested with GPT-Neo -2.7b and Llama 7b. Our results show that the quality of the LLM used for evaluation is the main factor in the final performance, while the choice of ranking LLM has less impact. Although combining the training data from two LLMs gives the best overall performance, we didn't use this technique in our main experiments to keep things simple. Section summary. LLM-R performs better on certain tasks than others, with knowledge-intensive tasks showing smaller improvements compared to average, except for the NQ dataset. The Squad V1 dataset shows worse performance due to limited diversity in retrieved examples, while the Sentiment 140 and MNLI datasets benefit from similar input patterns. The choice of LLM for task evaluation has a major impact on performance, while the ranking LLM has a minor impact, and merging training data from two LLMs yields the best overall performance. Section 6.5 Scaling the number of in-context examples and retriever size. In Section 6.5, we delve into the impact of scaling two key factors on the performance of our language learning model with retrieval, LLM-R, the number of in-context examples and the size of the retriever model. We found that the model's overall performance improves as we increase the number of examples it retrieves. However, the benefits start to taper off after the model retrieves 4 examples. When it comes to the size of the retriever model, we noticed something interesting. The smaller model's results were on par with those of the base-sized model. However, the larger model showed a more significant improvement in performance. These trends held true across the two language models we tested. Therefore, those using this model can choose the best configuration for their needs, balancing performance against computational cost. Section summary. In this section, the authors explore the impact of the number of in-context examples and the size of the retriever model on the performance of LLM-R. They find that increasing the number of retrieved examples improves overall performance, but the gains become less significant after 4 examples. Additionally, they observe that a larger retriever model leads to a more substantial performance boost compared to a smaller model. These trends hold true for both examined language models, and practitioners can choose the appropriate configurations based on the trade-off between performance and computational cost.